Hello everyone, in this segment we are going to now talk about set. So in this lecture we will talk about basic definitions of set, few operations that we can do on set, set identities and binary relations on set. So what is a set? So when we talk about set, like in our daily life also we often talk about set, like a set of books, a set of students, a set of object. What is a set? A set is an unordered collection of object. Okay, so the important definition here is, the important part of the definition is, a set is an unordered collection of object. Okay, so what we can do, like in a set we are going to have, a set means it's a set of object, or it's a collection of object. Let's see, we are talking about, let's see, we have a set of course like that. Okay, we use the opening and closing bracket, and in that closing bracket we are going to list the collection of object in a set. All right, so what we can do, we can define a set by directly listing all the elements. All right, so for example, here we have a set. We're going to use the name of a set equals to this opening bracket and closing bracket. Okay, and inside this bracket we can directly define the listing of all elements. Say for example, this is a set of some numbers 1 2 3 4 5 6 7 8. There are 8 numbers. This is a set of 8 numbers, and these numbers are listed in this set. So the second example, this is a set of few course number. You can see that these are few course number. So here we have some course. All right, 1130 2110, some courses are listed here. So each of the object in the set, they are known as the elements or members of the set. Okay, or we can say that the set S contains its elements. Now after we define a set, okay, after we define a set, the set becomes a single mathematical object. All right, and it can be an element of other set. So it's like a bag. Okay, it's like a bag. We can have multiple elements. When we go to shopping, we actually grab multiple objects, but as we have to carry them all with our one hand, what we do, we keep them all in one bag, and we can keep them with our one hand, right? So it's like a bag. So inside a bag you can have multiple objects inside a bag. After you have multiple objects in a bag, it becomes, this bag itself become one object. Okay, so after we define the set will become one single mathematical object. Okay, now S is one single mathematical object. So then the S can be also an element of set. For example, here we have a set. Say we have a set here. One set has 1 2, another set it has 1 3, another set has 1 4, like that. That's how I have 1 2 3 4 5 6 set, and each of the set all together can form another set. Okay, so here S is set. Now S set has 6 members here, and each of the members or elements are also set. All right, so how we define a set? So one way to show a set is by listing all the elements. Okay, just defining, listing all the elements. So sometimes it's convenient, but sometimes also it becomes impossible, okay, to define a set by listing all its elements. So another alternative way is that we can define by a set by describing its properties. Okay, describing its properties that the element should satisfy. So we use another notation. We use another notation like this. Okay. So the first notation we used here by listing all the elements. All right. But sometimes it's not convenient. Okay. Because in one set you can have a couple of lot elements. For example, I'm saying that S is a set of all odd positive integer number. Now S is a set of all odd positive integer numbers. Alright, what does that mean? So S can have 1, 3, 5, 7 and dot dot dot. That means I cannot actually end. I cannot, it's not possible that to list all the odd positive numbers here. Okay, so there is going to be a lot of numbers and it's not possible to list all the numbers. All right, and sometimes actually we cannot just possibly list all the numbers because probably by listing all the numbers we cannot say the what is the properties of each of the numbers. Okay, what is this set is about. So in that case we can use a different notation. In that notation this looks like this. Okay, and this notation is known as a set builder notation. So in this notation what we say, we define a set as like a set of elements x. X is a set of elements. All right, x is a set of elements in a, x in a, then okay, then we use another notation. This one is, we read it like that, such that. Okay, and this notation it's actually says that x in, for now we can say that x in a. Okay, this notation actually stands for member of a. All right, but for now we are going to read it like x in a such that p of x. P of x is actually, we can say that x satisfies property p. So here x is a set where this is a set. All right, this is a set of elements x. All right, x will be member of x in a such that x satisfies property p. All right, for example we want to say that x is a set. We are going to build a set, define a set where this is going to be set of all prime numbers and the numbers which are less than 1000. Okay, so we can build a set like that, x equals to x. All right, such that so until this it will say that x is a set of all prime numbers. Okay, now let's see, we are saying that s is a set of all prime numbers and all the number which are less than 1000. So we are going to write that and x is less than 1000. So here x is our elements of the set. Okay, so this will be read as a such that, and this one is our property. This is our property and all the elements of the s. Okay, all the elements of the s, the set which is x, will follow the property p. All right, so another example is that x is a real number and minus 2, x is x is greater than minus 2 and less than 5. So it means that x is a real number which is between minus 2 and 5. Okay, so that's another notation to define a set. There are some well-known sets. For example, let's see, we are saying that the set of all real numbers. Okay, so the set first to define a set of all real numbers, we can use some well-known set, and there are some notation to represent that. For example, this one will, when we're going to write it like that, this one means that the set of all real numbers. This notation stands for the set of all complex number. This notation stands for the set of all integer numbers. This notation stands for the set of all positive numbers. Okay, all positive and integer numbers. This is a special set, and this one is stands for empty set. Okay, for example, we are writing a set like that, so you can see that this is a set where we do not have any elements, so that means this is a empty set. This is an empty set where we do not have any elements inside the set. So in shortcut, we can write that the set equals to, this symbol means that it's an empty set. Alright, so initially we said that what is a set? A set is a unordered collection of object. Okay, so the order is not important in the set. So if we write that S equals to ABC, that is same as writing S equals to CBA. So think about that. I am saying that S, I'm talking about a set of students. Okay, so for a project I am going to use a set of students. Say for example, I am going to use for example, set of students is going to participate in one of my project, and they all have a name. So say student 1, student 2, student 3. Okay, now it doesn't matter in which order I am listing them. Okay, at the end they will always be the members of the student. So the order of the elements in a set, it's not important. Okay, it's not important. So I can represent the elements in the set in any order, they will be still the same set. All right, and the number of occurrences in the set also not important. Order is not important and the number of occurrences is not important. So in a set, if the single elements is present repeatedly, that doesn't matter. Actually, this will still be the same set. So if the set is A, B, C, and if I write A multiple times, any elements multiple times. Okay, so here we have A 3 times, but that doesn't matter, still it is the same set. Okay, so the number of occurrences in the set, it's not important. Okay, at the end we will say that S is a collection of object where the objects are A, B, C. Now how many times there is the A, okay, the A will be present, it doesn't matter. All right, the most basic important thing in the set theory, whether a element is in the set. Okay, so whether a element is in the set, so in which order they are present in the set or how many times they are present in the set, they are not important. Okay, all right. So each of the element that is in the set, they are known as a member of set. Okay, they are known as a member of set. So membership of a set means the elements of the set, each element of the set, they are the member of the set. Okay, so this is the notation we are going to use to denote the membership. Okay, so x is member of A, or we read it like that x is an element of A, or also we can read it like x is in A. We can also say that whether x is not element of A. Okay, say for example, in that case we are going to use this notation, member symbol and then not. Okay, it will be read as X is not an element of A, or X is not in A. Okay, say for example, if we have S equals to 2 3 4, so 2 means 2 is an element of set S. Now 5 is not an element of set S. Okay, so let's see P be the set of all prime numbers. Okay, let's see P be the set of all prime numbers. So in builder notation, we are going to write it like that: P equals to X, all right, such that X is a prime number. All right, then 97, it's a prime number, so that means that's an element of P. Okay, now how about 321? 321, it's not a prime number, so that means it's not an element of set P. Okay, so Q be the set of all rational numbers. All right, so then 0.5 we can represent that by 1 by 2. It's a member of Q. Now root of 2, it's not a rational number, so it is not a member of Q. Okay, so this one is our notation, is member of or element of a set. Okay, and this one is denote as not member or not element of a set. The size of a set is denoted as like this notation. So the set and then this absolute symbol. Okay, it is defined as the number of elements contained in set. So if the set is like that, we can just count the number of elements there: 1 2 3 4 5 6 7 8. So the number of elements in the set is 8. So here the number of elements in the set is 4. Okay, now what about this one? So in this set contains a set of set. Okay, so each of the elements are also set, but in this set, what is the number of elements? Each of the element are set. Okay, but the number of elements in the set is 1 2 3 4 5 6. So the size of the set is 6.